In grade 11, you probably taught that a continuous function is one where you can draw the entire thing without lifting your pencil up, right? Your pen. This is a continuous function in grade 11, but probably you might have been told that this one is discontinuous. Why would you be told that in grade? Because you had to lift your pencil because there's two different pieces, right? That is not going to be actually true here because we're going to have a more sophisticated definition of a continuous function. When we talk about continuous functions, first we're going to just talk about continuity at a single point. Is it continuous at this point or not? Then we'll talk about is the entire function continuous. When we say a function is continuous, so we're going to leave this saying a function is continuous for a few minutes here because of those difficulties. Continuity at a point. Continuity at a point is it continuous at a single point? If I create a graph that has a hole in it like that, it is discontinuous at that point. Or if I draw like the graph I did before here, like if I have this thing is going down like that, but then suddenly it's up here. If we have a grid on this one as well. So this is going to be 3 here. This one is not continuous at x equals 3. It's got a discontinuity at x equals 3. This one has a discontinuity at x equals 0, right? Not continuous at x equals 0. There's a discontinuity. There's those are two different types of discontinuities. Okay? When we get to talking about is this function continuous, our definition, I'm going to tell you ahead of time here, even though it might take a while to get it. Our definition of is this whole function continuous is going to be, is it continuous at every point on its domain? Is this function continuous at every point on its domain? What's the domain of this function if it can go to the right and the left here? All real numbers except 3, right? Here, the domain here is x cannot be 3, right? All real numbers except 3. Is it continuous here? Is it continuous here? Is it continuous at every point up to that hole? It is, right? It's continuous at every point on its domain. So the complication from grade 11 is this is going to be called a continuous function even though it has a discontinuity. Because the discontinuity is not a point on its domain. If it was defined at that point, now what's the domain of the thing? Now it's all real numbers, right? Now, is it ever discontinuous at some point on its domain? Well, now it's discontinuous here, right? Because now that it includes that point, it's discontinuous there. If you're moving along here, suddenly you jump up there, and then suddenly you're back down here, right? Whereas without that point, it's continuous at every single point here, and it's continuous at every single point here. It doesn't ever jump up to another value and back down here. This one, the domain here is x cannot be 0. It's continuous at every point on the domain here, and it's continuous likewise over there. It's not defined at 0. So even though there's a type of discontinuity there, when we talk later about is the function continuous, this is going to be a continuous function. Yeah, I can. The definition of a continuous function. I'll write it up above here. Continuous function is one that is continuous at every point on its domain. For every point that counts to that function, it's continuous, right? If you're going along getting 100% on everything in the course, then you do a quiz, you get 90%, but it's one that we aren't including. technically you could kind of say I'm still getting 100%, right? Because we're not counting that one. Okay, I don't know if that works here, but if this point is not included in the domain, even though it looks like from the graph there's a missing value there. If it's not a part of the domain, then it doesn't count. You only look at the domain of the function. What? Well, if there's a missing value there, like the function doesn't even exist at that point, it's not part of the domain. The domain of this function is all possible x values. There's no point defined at 3, right? There's an empty value. It's missing. That function, there's no value. If you had a graph of that on the calculator, you know how it says x equals y equals? When you get to 3, this would just be blank here. There's no y value for that. Whereas, I mean, I don't think you can graph stuff like this on the calculator, but if you had that, it would suddenly say, I don't know, whatever this is here, 4 or something. You'd be going along here and it would be, okay, it's 2, 2.5, and suddenly it jumps up to 4. Then it's, as a function, it has that big jump and back down again. Whereas if that point's missing, it just doesn't even exist. That point doesn't even exist, right? It's not part of the domain. We'll get it as we go here. I know that I put this up front just because I wanted to mention it, but later on we're going to talk about continuous functions or not. We should talk about discontinuity at points to start with and different types of discontinuities. Which points is this not continuous? It's where does it have a discontinuity? Now I'm not talking about whether the function as a whole is a continuous function. Right here, no, there's a definite jump, right? The values are going down here and suddenly they're up to there. That's a discontinuity. I'm not talking about is the entire function continuous or not. Right now, this is a discontinuity. This is a discontinuity. And the scale is a bit off on my picture there. It's right on yours. Something weird happened. Where else? Anywhere else? That's it, right? There's a sharp corner here, but that doesn't mean it's not continuous. What's the relationship between the limit and the points where these continuous or discontinuous points exist? If you want to say this is where it's not continuous, right? It's not continuous there. Let's just pick a couple of examples of where it is continuous. Continuous everywhere else, right? Everywhere else on the domain. For example, give me a couple of points where it is continuous. 3, wherever on mine, 3 is up there. I'm going to do 2.5. 2.5, I don't know. It's continuous there. Look at the relationship between the limit as you approach that point and the function value. If I start over here and I'm approaching this value here, 2.5, as I come from the right side of that, what's the relationship between them? What's the relationship between the limit as you get closer to 2.5 and the actual value at 2.5? I knew I shouldn't have picked that because I can't even tell on this graph. Let's do 1.5. Because then we can see what's the function value. F at 1.5, what is that? It's 1, right? What's the limit as you approach 1.5? 1. As you get closer to 1.5, the function is behaving the same way it actually is at 1.5. As you get closer to 1.5, let's pretend this was, I don't know about airplane, but if something is getting closer to approaching something and it's foggy, you can't see what it actually is when you get there. So let's say you don't know what the value is actually at 1.5, but as you get closer to 1.5, it looks like the value should be 1, right? The limit is saying what should it be as you get closer? It should be 1, and it is 1. Since those match, that's what continuity at a point is. Whereas, look at the other one here, which will have to be the next part. Look at the next one. Look at either of the two up above. Try and write the same kind of statement for these two, and you'll see that it doesn't work. Do the one for 2 first. Okay? Try and write a similar statement for 2. Look at what the function value is and what the limit is. Well, I put this in.